So let's talk a little more about modeling and the modeling process and how we build a model, because I want to build a slightly more complex model. And then our secondary goal is to use vector fields, and you'll see in this example how to use vector fields to get a real sense of what the model predicts. So let's go back to the world's simplest model, where, for example, X is the size of a population. Let's say it's the number of rabbits in our rabbit population. And the differential equation we're going to start with is what I'm calling the world's simplest differential equation, namely x prime equals bx, where b, you remember, is the per capita birth rate. So this is a differential equation. It is a model. It predicts a certain kind of behavior, which you can graph by just plugging this in and choosing an initial condition in SAGE. But the time behavior that's predicted by this model of rabbits as a function of time is that since the growth rate is always positive, the population is going to get bigger and bigger and bigger. And the rate at which it's changing is also going to get bigger and bigger and bigger, because the rate at which it's changing is proportional to the current population. So this is the prediction of this model. And in some respects, predictions are absurd. They're silly. Somebody once calculated that at the end, if this were the only thing in effect, at the end of 10 years, the whole solar system would be full of rabbits, and it would be, the rabbit ball would be expanding outward at the speed of light. Okay, so that's ridiculous. That's absurd. That doesn't happen. So if it doesn't happen, then this is not a good model, and we need to write a better one in which it doesn't happen. So, of course, when I say this is a bad model, all models are bad, but some of them are better than others for certain purposes. Now, you may remember, for example, back in high school, you put the bacteria in the petri dish, and the bacteria multiplied. And for a couple of days, it sort of did follow that law of, incidentally, exponential growth as predicted by that very simple differential equation. It did follow the law for a while. But the Earth was not overrun with the bacteria from your high school experiment. That would be an interesting premise for a science fiction movie, but it doesn't actually happen. There are instead limits to growth. And those limits to growth limit the growth of the bacteria on the petri dish, and they limit the growth of all populations. So we need to come up with a better model that has built into it the idea of limits to growth. So now we're going to say x prime equals bx. That's our original model. But now I'm going to multiply that by a limit to growth, which right now I'm just going to call it the limitation factor. And then we're going to have to figure out how do we write that limitation factor mathematically. So now we have to figure out how to put a mathematical form to that limitation factor. So we're going to start by assuming that the environment that these rabbits are growing up in has a carrying capacity. And this is a very common term in ecology. The carrying capacity is the number of animals that the environment can support. And we're going to assume here that that's just some number k, and k is going to be a number of animals, a number of rabbits in this case, that the environment can support. Now, if the environment can support k animals, and currently there are x number of animals, then the fraction x over k is equal to the total resources currently used. Or more accurately, instead of total, let me say the fraction of resources that are currently used. Because if x is equal to k, then the carrying capacity has been reached, and the fraction of resources currently being used is 1. So if x over k is the fraction of resources that are currently being used, then it follows that 1 minus x over k is equal to the fraction of resources that are available, that are not being used. And that quantity, the fraction of resources that are available, that's our limitation factor. The smaller that is, the smaller the growth rate is going to be, and the limitation factor is going to have a low value. And so now we are just going to take this, the fraction of resources, and that is going to be our limitation factor. And consequently, the new differential equation expressing the limitation factor is now going to be x prime equals bx times 1 minus x over k. And this is a very famous equation which is called the logistic equation. And this is now what I want to talk about. So let's take a look at this equation. Let's take a look at the logistic equation and try to figure out what behavior is predicted. We have a feeling it's not going to be infinite growth because we have built in that limitation factor. But now if you stare at this differential equation, you notice when you multiply it out, you have a square, x squared term. This is not an easy, you can't just stare at this equation and say, well, I see what it's going to do. So we have to be a little bit sophisticated, but the vector field math that we've learned is going to do us a big favor here and is going to tell us how to understand the behavior of this system. So just to fix ideas, we need to pick some values for these parameters. I'm going to pick b equals 0.2, which is that saying that 20% of the population is giving birth in any unit of time. Let's say we're working in years. And I need a carrying capacity, and the carrying capacity I'm just going to posit to be 1,000 rabbits. So now we have a definite differential equation. X prime equals 0.2x times 1 minus x over 1,000. And we can go to work. So the first thing we do is we draw state space. And state space is, in this case, positive or non-negative x space for the number of rabbits. Now, I want to take just a random point in state space and calculate the vector field at that point. Let's just pick the point x equals 15 right there. and I want to calculate the vector field. So the vector field at the point x equals 15 is x prime equals 0.2 times 15 times 1 minus 15 over 1,000. So what is that? 0.2 times 15 is 3. 1 minus 995, 1 minus 15 over 1,000 is very close to 1. Let's say it's around 0.95. This is going to be 3 times 0.95. It's going to be around 2.8. So that's our change vector. X prime is 2.8 at the point x equals 15. Okay? Let's take the point x equals 90. Let's ask what the change vector is there. Well, at the point x equals 90, x prime, this is our first calculation, x prime equals 0.2 times 90 times 1 minus 90 over 1,000. So that's 0.2 times 90 is 18 times, this is 0.9. So 18 times 0.9 is around 16. Let's call it 16. So at the point x equals 90, we have a bigger change arrow, which is x prime equals 16. So we see that for low values of x, the vector field is moving to the right, which means that the population is increasing. Great. Now, let's take another point. Let's take the point x equals 2,000. And let's ask what's the change vector at the point x equals 2,000. Well, it's going to be 0.2 times 2,000 times 1 minus 2,000 over 1,000. So 0.2 times 2,000 is 400 times, look at that, 2,000 over 1,000 is 2. 1 minus 2 is minus 1. So the change vector at the point x equals 2,000 is the change vector minus 400. And so now the change arrows are going, for large values of x, the change values are negative. And as you see, the bigger the number you plug in here, the bigger this negative sign is, and it's just going to get bigger and bigger and bigger, always pointing to the left. And that's going to be true for all large values. And as you might suspect, if it's positive for low values and it's negative for high values, you're going to ask the very intelligent question, which is there a point in there at which the change value is 0? And the answer is yes. Obviously, if x equals 1,000, then I have the term 1 minus 1,000 over 1,000, but that's 0. And the change vector, since that's 0 multiplying everything else, the change vector there gives us x prime equals 0. And so we get a very nice picture of the total change in the system just by calculating a few change vectors. And the change vectors tell us that the population will grow from a low value, that growth will accelerate until it reaches near this point. Then it's going to get smaller and smaller and smaller. It's going to be 0 at that point. And then it's going to pass to negative, and it's going to get more and more and more negative as we get larger and larger values. So the behavioral prediction is that no matter where you start in this system, you're going to end up at x equals 1,000 and sitting there forever because your change vector at that point is 0. So let's be absolutely clear about what we're talking about here. This here is the point x equals 1,000. That says 1,000 rabbits at this point. And when we plug that x value into the x prime change equation, that's when we get the answer x prime equals 0. So this point, both of those things are true. X is 1,000 and x prime is 0. You will learn that this is called an equilibrium point of the system. We'll talk about that in a week or two. But for now, let's just note that at this point, x equals 1,000 and x prime equals 0. So where will this state point, where will the system go from this state point a year from now? And the answer is it will go nowhere. It will go nowhere because x prime equals 0. The change in x equals 0 means x doesn't change. Doesn't mean x is 0. It isn't. It means x doesn't change. Now there's this other point here, the point x equals 0, where x really is 0. And if you plug x equals 0 in here, you immediately see that x prime equals 0 again. So there are really two places in state space where x prime equals 0, namely x equals k and x equals 0. X equals 0 certainly implies x prime equals 0 by plugging it into the equation, and this gives us the not entirely earth-shattering fact that if you have no rabbits in this model, you will always have no rabbits in this model. Now, that's not 100% trivial because we are assuming that there is no infestation, there is no import term. There are no rabbits immigrating into the territory of this model. The only rabbits we're going to have in this model, that's what the assumption is that the only rabbits in this model are the rabbits that are going to come from the rabbits that we put there as an initial condition. And if that number is 0, regardless of the birth rate, there is always going to be 0 rabbits in this model. So 0 is another equilibrium point because the change is 0. Just to check our ideas, we deduce that the vector field is going to look like that. It's going to all head into the point x equals 1,000 as an equilibrium point. We can check that by also just running the simulation in Sage. What does it look like as a function of time? So if I write here is x as a function of time, and I'm just going to put the point x equals 1,000 right there, then what Sage will tell you, and it shouldn't surprise you by staring at the vector field, is that if we start any x initial below 1,000, not of course 0, but if we start with 1 rabbit, let's say, then the number of rabbits is going to increase. The rate of change is going to get bigger until the rate of change starts to get smaller, until the rate of change is 0 at the point x equals 1,000. So that the time graph, or the time series that you would get from Sage, from starting your value below 1,000, is it would rise to 1,000 and then saturate there. Similarly, If we start with an initial condition above 1,000, then the rate of change is always going to be negative. The slope is always going to be negative. And we're going to go to x equals 1,000 that way. So those are the two time behaviors that are predicted by this model. And you can see where that comes from on the vector field immediately.